Hello, everyone. Welcome to the 10th lecture of probability and stochastic process. We start with solving the previous quiz. So you can see here that we have the problem that we have x of t is a random process given by x of t equal to alpha times t plus 1. And alpha is a random variable, follows zero mean normal distribution. Then the question is x of t stationary or non-stationary, okay? And find the mean and autocorrelation function of this random process. Okay, let us go to the whiteboard to see how to handle this problem. So we have here that it was given that x of t is equal to alpha t plus 1. And alpha is normal distribution and has zero mean and maybe unit variance, or let's say that it is variance sigma square. Okay. So first of all, that we can compute the mean of x of t. So the mean of x of t equal to the mean of this value alpha t plus 1. And we can distribute the expectation operator inside. So it becomes, we have only one random variable here is alpha. T is the time. Time is deterministic, okay? So it becomes like expectation of alpha times t plus
عفوا
1.
دكتور عفوا دكتور هي الفا اكس تي تقريبا.
No, it was alpha times t.
Times.
Yes. Okay, no problem. No problem. It was if you solve it as alpha xt, it will be no problem. No problem. Okay. Okay. Let us do it in this way, and then we come back to that it is alpha xt. Okay. So and now this the expectation of alpha is equal to 0. Then the mu x in this case equal to 1. Okay. So above the mean, it is stationary in mean, because the mean is not depending on the time t. Okay. But if we look to the autocorrelation function, the autocorrelation function here, xx of t1 and t2 is equal to the expectation of x at t1 times x at t2. Okay. And in this case, if we take this now, expectation of x at t1 times x at t2, and x at t1 equal to alpha t1 plus 1, and x at t2 equal to alpha t2 plus 1. Okay, so now it becomes like expectation of alpha square t1 t2, okay, because you multiply those together, okay, plus alpha t1 plus alpha t2 plus 1. And if we distribute the expectation, so we will have expectation of alpha square t1 t2. This will be 0, this will be 0, and will be plus 1. So the expectation of alpha square, it was given like sigma square or 1. It depends on the probably was it unit variance, or if it was not given as it is unit variance, then just you use variance sigma square. If it is 1, then you can put just 1. So t1 times t2, which means that in this case that it is not stationary in the autocorrelation. So in that sense, x of t is not stationary, stationary process, and this will be the autocorrelation function between t1 and t2. So the autocorrelation depends on the time t1 and depends on the time t2. If there's a question, you may repeat it, Dr. Farhat, because I didn't hear.
دكتور مش هي يعني الاي مش موصلة على القوس جوا؟
Yes.
الاي
Yes.
constant مش هي اي ايوه plus 1.
Yes, because when you distribute this inside, it becomes like expectation of alpha square t1 t2. The time is not random variable. A plus expectation of alpha times t1 plus expectation of alpha times t2 plus expectation of 1 is equal to 1. And this 0 and this will be 0.
يعني قصدي في الار اكس 6 المفروض
yes, this one. Yes, you are right. Yes, this one. Yes. Thank you. So if we go back to the as you understood the problem, you said that you understood it like x of t equal to like alpha x of t times t, isn't it?
Yes.
Plus
x of t.
plus 1.
And this plus 1. Is it this way?
No, here alpha x t of t.
Alpha xt.
So there is no t here.
Yes.
Okay. So in this case, if you take x of t as a common, so it becomes x of t 1 minus alpha equal to 1. Okay. So in this case, x of t equal to 1 divided by 1 minus alpha. Okay, so of course, if you understand it in this way, this is clear that it is not it is stationary, because we don't have the time at all here. It becomes now not random process. Now it is because alpha, it was given as a random variable. So in this case, the expectation of x equal to just the expectation of 1 minus 1 minus alpha. Okay, and then the expectation of x squared, you can see that it will be expectation of 1 minus 1 minus alpha squared. So in this case, actually, you cannot say that it is a random process at all, because we don't, the time now is not exist at all here. So if you solve it in this way, of course, it will be stationary. The process will be stationary because it is not depending on time. It is not depending on time. Okay, it is just like because it is independent of time, then the distribution or the mu of x and rx of x and the variance of x, all of them will not be function in time. There is no time here. There is no time here. Okay, so in that case, of course, it is stationary. If you assume it in this way, it will be okay. I will assume that it is correct. Okay, if you solve it as that it is a stationary process. Okay, the second question, it was that we have like channel, while it's a channel, and the signal to noise ratio, it was given like is a random process because it changes with time, and it has a known probability density function. So we don't know the probability density function of the SNR. Okay, and but looking to the history, we found in that channel that the expected value of this SNR equal to 3. So the average equal to 3. The question was, what is the probability that SNR will be greater than or equal to 30? To be greater than or equal to 30. And of course, because we don't know the distribution of the SNR, then we will have just bound. So the upper bound, it means that this value should be less than or equal to something. Okay, actually this was given, if you look to the, let me go to the yes, if we go to the problem here, yes, so you can see that it is given, known as Markovian inequality. So in Markovian inequality, because the signal to noise ratio is always positive, the signal to noise ratio cannot be negative. Okay, so the Markovian inequality says that the probability, the upper bound of the probability that x to be greater than or equal to a is the expected value of x divided by a. So it will be in this case like 3 divided by 30. So this probability will be less than or equal to 0.1. Okay, so this is the solution of the second quiz. So it is just direct substitution in the equation. So it will be 3 divided by 30, which is equal to 0.1. The last problem is that y equal to xk plus 0.5 xk minus 1 plus 1. And this is the autocorrelation function. And they say that xk, it has 0 mean. And this is the autocorrelation function given for xk. Okay, let us see how to handle this one. So we have yk equal to xk plus 0.5 xk minus 1 plus 1. Okay, is it correct in this way?
Yes.
So and now we want to compute the mean. So the mean of this y of k, expected value of y of k, equal to the expected value of xk plus 0.5 xk minus 1 plus 1. And this equal to expected value of xk plus 0.5 expected value of xk minus 1 plus 1. And they say that it is a stationary process, which means that, and it is 0 mean. So the mean is not function in the time. So in this case, this will be 0. This will be 0. And then the mean of yk equal to 1. This is the mean. For the autocorrelation, it will be the expected value of yk times ym. This should give you the r y of k and m. Okay, and this will be the expected value of, you multiply those together, so it will be like xk times xm. I just show you how I did it. So xk plus 0.5 xk minus 1 plus 1 times xm plus 0.5 xm minus 1 plus 1. So this will be xk times xm. Sorry. Just lost the page. Can you see the? Where is that? Yes. Okay. So and now we multiply, so it becomes expected value of xk times xm. Sorry, xm, and plus. Okay, 0.5. It becomes xk times xm minus 1. Okay, and plus xk. Okay, plus I'm trying to do it step by step, so it becomes 0.5 this one times this 0.5 xk minus 1 times xm. Okay, and plus 0.25 times xk minus 1 times xm minus 1, and plus 0.5 xn minus 1, and finally it becomes plus, and you multiply 1 in each of those, so it becomes plus xm plus 0.5 xm minus 1 plus 1. Now when you take the expectation inside, each one, that, for example, expectation of xk is equal to 0, expectation of xm is equal to 0. Okay, and when you have multiplication, for example, expectation of xk times xm. Okay, so we know that it was given that r xx, they say that it is stationary, and it will be like 0.5 of the power of k. So now when you have k and m, okay, so you made it like this way, so it becomes like 0.5 times of the power k minus m. Okay, so the expected value, I repeat it, I do it here again. So the expected value of xk times xm equal to 0.5 of the power k minus m in this way. Okay, and for this one, again, it becomes 0.5 of the power k minus m minus 1. So it becomes like k minus m plus 1. Take the absolute. For this one, the same. It will be 0.5 of the power k minus 1 minus m. So it becomes k minus m minus 1. Okay. And this one, it becomes 0.5 when we take the expectation of the power, absolute value of k minus 1 minus m minus 1. It becomes plus 1. So it becomes like k minus m again. Okay. And so on. So this is the way how to, when you distribute this expectation inside. So you just use the value which was given in the example itself. Okay, so yes, yes. Let's go to that. Yep. So as you can see here, so if I just take the common, yeah. So you can see this is the Rxx of k, and you can see that it is x is y since stationary. Why it is stationary? It means that the autocorrelation depends on the time difference between the two samples. So when you have Rxx of, let's say, L and M, so simply it becomes 0.5 of the power of the absolute value of L minus M. This is the meaning of White's stationary in autocorrelation. So it depends on the time difference, not on the time itself. At what time? Okay. So by this way, we can find the autocorrelation and of y, and as well as the mean of y. Is yk stationary or not? Of course, it is stationary. Of course, it is stationary. And remember, when you have a stationary signal for any linear system, the output, and it is time invariant, so the output will be also stationary. But what if you have here, if I give you this, but I give you like yk equal to is the same xk plus 0.5 xk minus 1, and then a plus k. So now we still have linear system or linear difference equation, but now it is not time invariant. It depends on time k. So in this case, it is not necessary that the output will be stationary. The output becomes non-stationary here, because if you take the expectation of yk, you will have 0, 0, but then the output mu k or mu y equal to k in this case. And k in difference equation representing time. So this k represents the time. And in this case, yk will not be stationary if you have the time symbol in this way. Okay, but this one, in this example, yes, it is stationary. Okay. Do you have questions about this? Okay. Now, if we go to the last lecture today, the topic for the last lecture today, it will be what is the impact of linear or with random process when it is input to linear system. Okay. Yes, this is Markov process. We have already seen it. I have added some examples for the Markovian as well, and you can see that I added one example related to modeling channel, so you can see it. And for this Brownian motion, of course, as I said that it is not it will not be included in this course. And now, modeling of dynamic systems. I will introduce at the beginning just very fast review about linear systems, okay? About linear systems, the basics of linear systems, okay? So systems usually can be divided into two kinds of systems. So we have a static system and dynamic system. A static system, it means that the output, as you can see, the output, for example, here, y of t, depends directly on the input. So when you have certain input, x of t, if x of t equal to 1, then y of t equal to a plus b. If xt equal to 2, the output will be 2a plus b. If x of t equal to minus 1, y of t equal to minus a plus b, and so on. So this kind of system, we can say that it is like static system, so that it is not dynamic system. Or we can say that it is memoryless system as well. So the output depends directly on the input. So if we go to the talking a little bit over the whiteboard. Yeah. So we can see here that one example of the system which is memoryless is this circuit, the output of t, and we here have the input of t. Here we have R1 and R2. So we can say that the output equal to the input times R1 divided by R1 plus R2. So now any change in the input, it will be scaled to be the output. So the output actually is a scaled version of the input, just a scaled of the input. So if R1 equal to R2, then the output will be half the input. That's it. Okay. So this is static system. We don't have dynamics here. We don't have memory here. Okay. But if the circuit was a little bit different, like if we have this circuit now, okay, and we have capacitor and R. So in this case, we cannot say that the input or the output depends only directly on to the input, because when the input is there, so the capacitor will save or will change will charge at certain value, and then the output actually depends on the current input, but also depends on the history of the input. How was the history of the input? So if the input in the history, it was 0 for a long time, and the initial voltage here was 0, and then the input is changing, let's say with some value, then the output will have certain shape different than if that before that the signal, for example, was this way. So because the previous here, before this time, the time of observation before this time, it makes a change for the output. So in that sense, we cannot say that this system is static. The system is not static anymore. Okay, so the current which can go in this capacitor depends on the rate of change of the voltage here. So the current, as we increase the rate of change, the current will increase, which means that the current goes through the capacitor. It will be like C dV over dt. Okay, and this will be the output. Okay, so and in that case, if the current output equal to 0, for example, which means that this current will be also the same current which drops over the voltage. So which in this case it means that VI minus C the dV output over dt. This is the current. So this to the output, this will be the output. So now the output actually, we have differential equation now. We have differential equation which could be represented like C dV output over dt, okay, minus V input, okay, if we take this in the other side, okay, equal to, or then it becomes plus the output equal to 0. So now we have differential equation, first order linear differential equation representing this circuit. So we have memory now. We have memory in this circuit, so we cannot use the previous static equation anymore. Okay, so now to solve this equation, it means that the output depends on the history of the previous like input. Okay, so how could we handle, or what will be the output if we have here like random process input? If we have random input to this circuit, how will be the characteristics of the output? Okay, before we go there, it is important to ask ourselves why we need this. Actually, the reason for that, you know that this is low pass filter, okay? And now we have actually the input, this input, the x of t. Usually we have either information, it means that the signal comes from, let's say, from microphone, or we have noise. So it can be information signal or it can be noise. Both of them are random. Both of them are random signals. I know that in your bachelor level, you study this signal when the input is only sine wave, for example, or if the input is just like a ramp signal or whatever. But actually, this is only to understand how this circuit works. But in reality, no one is interested to send like unmodulated sine wave. So if it is unmodulated sine wave in general, okay, it is sine wave. It has cosine, for example, it has certain frequency, it has phase. Okay, the output, it will change the magnitude and only the phase, and it will be the same frequency. Okay, what information we will get from that? Nothing actually, more than this simple like change in the magnitude and phase. But in reality, the real signals are random. If you know the signal exactly, and if you can predict the signal, it is not information. If you know the signal and you can predict it exactly, for example, if I give you that x of t equal to exponent minus alpha t, okay? So now, at any time in the future, I can expect what will be the signal. So I know that if t this in second, for example, then I know that x after 100 seconds, it will be e minus alpha times 100. Okay, there is no information here. No one is interested in such kind of signals. In reality, we deal with information. Information means it is a random signal. It is unpredictable signal. Actually, the information content is inversely related to the probability about the expected probability of the information itself. I mean that the information content for any simple k is related to 1 divided by the probability of k. It means that if you don't know the symbol, or you don't expect as less expectation of the symbol, as more information you will get from that symbol. So if you take the logarithm for this signal, or for this value, if you take log 2, for example, for 1 divided by pk, so if you exactly know the signal, so the probability that to predict the signal is equal to 1 divided by 1 equal to 1, the logarithm of 1 equal to 0. It means that it has 0 information. It has 0 information. If you know the packet 100%, then it has 0 information. Okay, so if the probability of packet to be happen is very small, then 1 divided by this probability is very large, and then the information content will be high. So if I informed something to you that, for example, if today you told me that the temperature in Benghazi today, it was minus 20. So what is the likely that this will happen? This probability is very small. This probability, it can be like 10 of minus 5, okay? Because it's very small probability to be minus 20 degree in Benghazi. in this time of the year. Okay, and it has been never been that like low temperature. Okay, so but if this happened, so the information content, if you informed me that, will be very, very high. Okay, but if I told you that the temperature in Finland today, for example, was -20, it is not that big surprise, because it's expected that to have -20 in this time of the year in Finland. So this is the difference. So as if you cannot expect, or as lower expectation of the signal, it means that it carry more information. Okay, so the signal itself is random. Any signal here is random process, either noise or information. It is a random process. So it is important to deal with random process in case of linear systems and also in non-linear systems. So this is the reason that why we need to have this kind of analysis. Okay. If we go back to this simple circuit, as I said that maybe today is slightly just we revise some basics, maybe from circuit theory, from linear system, before we come to the content of the course itself. So here we have R and we have C. You know that what is the capacitor? For example, the capacitor is two conductor plates, and separated by what? Separated by isolator. So here we have isolator. Okay. So it means that if you connect some battery here, DC battery, which has like plus V, what will happen? Actually, when you connect this plus V, the free electrons here, the free electrons will be attracted toward the positive battery polarity. Okay, so what you will have here, you will have plus ions, or the plus like atoms. Okay, and in the same way, the electrons here, because here we have positive, so they will attract by electrical power, they will attract more electrons here, so they will come and fill this the other plate. Okay, so if you have some ammeter here to measure the current flow, you will see that there will be a flow of the current for very short time. For very short time tau, there will be flow of the current, but then after that, the current becomes zero. Once this becomes plus and this becomes minus, then there is no any current will pass anymore. Okay, but now if you change the polarity, if you change the polarity of this battery to become like, now we have this becomes minus and this becomes plus now, what will happen? Since now we change the polarity, so we have minus V here. So we said that this was positive. Okay, and then the electrons here, free electrons, will be attracted again to the positive. Okay, and the electrons here, the extra electrons, will come back to the positive polarity. So the current will flow again, but in the reverse direction. Okay, what is the current flow here? How much the current flow actually depends on the rate of changes of this polarity. So as you change this polarity faster, as on the average, you will have more flow of current. This is the reason, this is the physical reason why the current on the capacitor is given by CdV over dt. This is why we have this differentiation, because the differentiation means the rate of change. So the rate of change of the voltage, it will cause like more current to flow in the capacitor. Of course, the maximum current that it can flow is determined by the resistor R. Okay, so now this is the physical concept why we have differentiation here. But still, this capacitor, because it saves the last current, it is saved there. So in that case, we can say that this circuit, it has memory. The same thing, it will happen for the inductor. But the inductor, it will have different concepts. The inductor is based on the magnetic field, not the electrical field. So when there is current here, there will be like a magnetic field in the reverse direction of the current, and they will try to like resist the current flow. And again, here the voltage drop is equal to L di over dt. So as we change the current, then we can have more like this is the voltage drop over this inductor. Okay, because in the beginning there will be resistance, but after that it will like collapse and the current will flow and the voltage drop will be zero. So the voltage drop will increase as the change of the polarity of the current will increase. Okay, so now after this like fast review of some very basic concepts, let us see one more thing. What is linear system? When we say that we have linear system. Linear system, it has one interesting property, which is called superposition. What is the superposition? Superposition says that if you apply x1 as input, and the system gives you y1, and you apply x2, and the system gives you y2. So if you apply a x1 plus b x2, the linear system gives you a y1 plus b y2. This characteristic is called like a superposition. Okay, and here we assume that it is time invariant system, which means that the system is not changing the characteristics with time. Because if the system changes the characteristic of time, then we have time variant system, which can be more complicated to analyze. But this is the concept of superposition. Okay, before we go further in this linear system, I give you simple example of simple time varying system. So now, if you have such like voltage divider with R1, but R2 is time varying, and then you have sorry, you have applied V input and then you have V output. Here V output equal to R2, which is actually function in time, divided by R1 plus R2, which is function in time, times V input. So this will be V output. Okay, so now if this R2 changes, makes the output change. So what that mean? If you put here DC input, and DC input, it has frequency equal to 0. But if you change this R2, then the output will be something else. So the output, it cannot be DC in this case if R2 is not fixed. So for example, if this is V input, like DC voltage V input, the output can be following somehow the changes of R. So now even we have the frequency equal to 0 at the input, now the frequency of the output is not 0. So time varying system can change the frequency of the input signal. But for linear system, even by the way, this one is linear system, but linear and time varying. So you always remember that the system that you study in linear system, that it will not change the frequency of the input is only linear and time invariant system. So, but if the system is time varying, the frequency can change. Okay, so now let us talk about linear time invariant system, where the system will not change the frequency of the input, and now this will be the superposition of property. Okay, now there is one thing interesting. For any system, we need to define some stem signal. What is the stem signal? A stem signal is the signal where I can formulate any other signal based on that signal. What I mean? In the system, if we assume that we have signal like stem signal, let us call it like S, stem signal of T. And I know the output. So the output of this signal, I know it. So it is Y of T. It will be based on this S. If I can represent any other signal X of T based on this S of T, then I will be able to determine Y of T for any X of T, because I know the output of this S. I give example. If we have the stem signal, let's say that it is X1, and X1 gives us Y1. Now I have another signal X2. X2 is equal to 3X1 minus, let's say, okay, let us say in the beginning that X2 equal to 3X1, just this one. So now I know that the output, because I know that the output when X1 is there is equal to Y1, then the output for this X2 will be 3X1. So it will be 3Y1. It will be 3Y1. Because X1 gives Y1, then 3X1 gives us 3Y1. Okay, let us take another one. So if X1 gives Y1 and X2 gives Y2, and now I have a new signal X3 equal to 3X1 minus 2X2. What is the output? If your system is linear system and time invariant system, then the output in this case will be 3Y1 minus 2Y2. That's it. So once you have this stem signals, if you know the output based on some signal, then you can have the other signal. So this property is very important in linear system about superposition. Okay. Now I will talk about our famous stem signal. Our famous stem signal is known as direct delta. The direct delta is given basically like that. We have this T, and then we have take it. Of course, they are different definition, but I will take the simplest definition. So it is from minus tau over 2 up to tau over 2. Okay. So the width of the signal is equal to tau. And the height of the signal is equal to 1 over tau. So the total area here, if you take the integration, if we call this like, let's say, call this delta of T, if you take the integration from minus tau over 2 to tau over 2, okay, delta T dt, the area here equal to 1. So this equal to 1. Because the width is tau, the height is 1 over tau, okay? So when you multiply them, so the area will be 1. So the area of this delta T equal to 1. Now, what happens if you reduce the size of tau? So if you reduce the size of tau, let us take like maybe another color. Okay. So now if we reduce the size of or the width tau, then we have something like that. So now the tau becomes smaller, then the height will increase, but the area is still 1. What happens if tau goes to 0? Okay, then we will have a very narrow impulse like this one. It will be very narrow impulse, and the height will go to infinity. Okay, but the area is still 1. So now delta of T, we can define it like equal to undefined or infinity at T equal to 0 and equal to 0 elsewhere. Okay, but the integration of delta T dt equal to 1. The integration from minus infinity up to infinity. Actually, it is not needed the integration to be from minus infinity up to infinity, because the signal is only exists in very close to 0, like here. So we can say that even the integration from 0 minus to 0 plus means that very close to the 0, but 0 minus, it means that you're approaching the 0 from the negative side. 0 plus means that you approach the 0 or from positive side, and the integration, the area of this delta is equal to 1. So now we have this interesting signal, or interesting, sometimes they call it direct function or direct delta function, but actually it does not function. It does not function in strict sense. Okay, but this signal, it is like impulse, like very high impulse, which can be like lighting, for example. It can be for very narrow time, can be like a nanosecond, and it has very large energy, but because the time, sorry, very large power, but because the time is very small, so it will have finite energy. It has finite, because the energy equal to power times time. So even the power is very large, but you multiply in nanoseconds, so the energy will be finite. So here we can, this is good approximation for the direct delta function or delta signal. Okay, so this direct delta actually is our stem in linear system, or in linear time invariant system. Why? Why this direct delta is very important? Actually, it has two properties. One property is it is a frequency domain. If you convert this delta of t in a frequency domain, so the frequency domain here for delta is equal to integration from minus infinity up to infinity, then it becomes delta t exponent of minus j2 by ft dt, and this equal to 1. So it means that the frequency domain of delta is equal to 1 for all frequencies from minus infinity up to infinity. This property is very important. Why? Because if we apply this delta of t for any system, okay, in the frequency domain, it will give you the response of this system for all frequencies. For any frequency, it will give you the, so you can know the system response for all frequency f from minus infinity up to infinity. So this property exists only with delta function. Okay. The second property, which makes delta is very important, is that now if you take this delta and you shift it to the right side, for example, or to the left side, doesn't matter. So we have time t here, and now I shift it to the sorry. Okay, it was switched off there. Okay, no problem. I will repeat it again. So now we have this time t, and then we have this direct delta somewhere here, okay, at time lambda. Okay, so now this delta is represented like delta of t minus lambda. It was shifted to the right by the time lambda. Okay, what will happen if you multiply delta of t minus lambda by any signal x of t? So we have another signal now, x of t. When you multiply them together, because this delta actually equal to 0 everywhere except at lambda. So the output of this multiplication will be what? Will be delta of t minus lambda times x of lambda. Okay, because now anywhere else the output will be 0. Anywhere else the output will be 0, because we multiply here 0. The signal after lambda is equal to 0. The signal before lambda equal to 0. And the multiplication will be delta of t, this one, minus lambda, this one, times lambda, times x at lambda. So it is only x at lambda, which is important now, because this one, this point is x at lambda. Now, if you take the integration of this signal, and you take the integration from minus infinity to infinity, or from lambda minus and lambda plus, but we get general, so minus infinity to infinity, x of lambda في delta of t minus lambda dt, we take the integration with respect to t, so you can see that x lambda is not function in t, so you can take it outside, so it becomes x of lambda integration delta of t minus lambda dt, and this integration we know that equal to 1. Okay, so it means that the integration from minus infinity to infinity x of lambda phi delta of t minus lambda dt is equal to 1. Sorry, equal to x of lambda. Equal to x of lambda. This property of delta, maybe you take it in digital communication course, is called sampling property. It's called sampling property. So if you want to take any sample from the signal at any time, you just multiply this signal with delta shifted by the time that you want to take that sample, then you make the integration, then you will get the signal at that time. Okay, so this is actually very, very interesting property. This one, what happened now if we replace the integration and make the integration with respect to lambda instead of t, and replaced lambda by t? So what we will get? So we can now, if we just replace this, we will have the integration from minus infinity to infinity, but this as x of t, just replace t with lambda, and this becomes delta of lambda minus t, and this becomes d lambda. Actually, this will be x of t. Okay, so x of t can be represented as summation, because integration is summation, is as a summation of many delta which is just like scaled by the values of xt. Okay, now if we apply this delta of t, now we know that delta of t can be stem function for any signal. So any signal can be represented as summation or as shifted summation of delta of t. Okay, now if we apply delta of t to a system, and this system gives me certain output, y delta of t. This output, or this response for delta of t, we know it as impulse response, as impulse response of the system. So when you have any system and you apply delta of t as input to the system, the output is called the impulse response. It is clear, impulse response. So the response of the signal if you apply impulse. And the impulse, as I said, it has infinity frequency. So all modes inside the system will be responded to every frequency at the input. So in that case, we call this output as h of t. We call it h of t. So h of t is the impulse response of any system. Is the impulse response for any system. Okay, so this h of t, actually the output of t is the integration of h of lambda times delta of t minus lambda times t lambda. Okay, so in that case, so we will have the output that it is y of t, which is the impulse response h of t. Okay, so if we see here that x of t can be also represented as summation of delta of t, and I know the response of delta of t for the system, which is known as the impulse response h of lambda minus t, then we can actually define the convolution. So this is from where the convolution comes. The convolution integral, it says that the output for any system y of t equal to the integration from minus infinity to infinity x of t, or x of lambda actually, times h of t minus lambda d lambda. So this is actually the convolution integral from where the convolution comes. Convolution comes from that, as I show you now. Okay, so now h of this h is the response for delta. Okay, so for delta of t. So in that case, you can represent the output as an output of this y. So this y could be represented as the convolution integral, which is given by this famous convolution integration. And now if we compute this signal in the frequency domain, y of f, then it will be x of f. I am not going to approve these things because it is linear system theory, but you can go back to this linear system theory course. So it will be the multiplication of x of f times h of f, where h of f actually is the frequency transform of h of the impulse response, and x of f is the Fourier transform of x of lambda. We have one thing here, problem, that when we have random process, x is a random process, we don't have Fourier transform. It is random. How could you find Fourier transform for random signal? Okay, so instead of using that directly x of f, we use what is known as power spectral density. And the power spectral density was given like psi xx of f. And we said that this is the Fourier transform of the autocorrelation function Rxx of tau. Okay, in that case, the output, we can determine the output Bose bucket density. So the output Bose bucket density yy of f equal to this h of f, the Fourier transform of h square. You take the absolute square times phi xx of f. So if you have the Bose bucket density of the input, then you can find the Bose bucket density of the output by multiplication with the magnitude value of the transfer function of the system square. Okay, and in that case, we can know what will be, for example, the bandwidth of the output signal. If you know the bandwidth of the input signal, when it is applied in some filter, then you can determine how will be the bandwidth, what will be the characteristics of the output signal. And also, actually, you can compute the autocorrelation of the output signal. So the autocorrelation of the output signal of any linear system of tau. Here we assume that it is stationary. Okay, so this will be the inverse Fourier transform of y of psi y of f. So when you take the inverse Fourier transform of the output Bose bucket density, actually you can get the autocorrelation function of the output. You can get the autocorrelation function of the output. Okay. One thing more. Let us now go back to the convolution, the relation. So we have y of t. We said that it is equal to the integration of x of lambda times h of t minus lambda d lambda. This will be the convolution integral. Okay, and this, by the way, it is the same to say that it is the integration of x of t minus lambda, okay, times h of lambda d lambda. It is the same. Okay, and in that case, assume now that x is a random process. X is a random process. Okay. What will be the mean of the output? Now I am looking for the mean mu y equal to the expectation of y of t. Again, we apply the same concept. It will be the expectation of the integration x of t minus lambda h of lambda d lambda. Okay. You can take the expectation inside this integration. And always remember this, always put the expectation where you have a random variable or random process, because the expectation of any deterministic signal or number is the same. So it will not change. So, but when you distribute the expectation inside, put the expectation only where you have the random signal. The random signal or the random process that we have only is this one. So this will be the integration of the expectation of x of t minus lambda, okay, times h of lambda d lambda. This will be the output mean. Okay, what is the expectation of t minus lambda? Now let us talk not stationary or non-stationary. Let us talk about non-stationary in general. So for the non-stationary signal, the expectation of x of t minus lambda is equal to mu x of t minus lambda. Yes, mu x is not random anymore, but still it is function in time. So in that case, this will be the result, will be the integration of mu x of t minus lambda times h of lambda d lambda. This will be mu y, and in this case, mu y will be t. So if x of t is non-stationary, if x of t is non-stationary with non-zero mean, and non-stationary, then the output will be also non-stationary in this, as it is shown in this equation. Okay, what if x of t is stationary? What if x of t is a stationary process? Stationary process. What will be the output? If it is a stationary process, we know that mu x of t minus lambda equal to mu x. It will not be function in time because it is stationary. So in this case, the output of mu y will be, since it is not function in time, we can take it outside the integration. So it becomes integration mu x times the integration of h of lambda d lambda. What that mean? It means that the output mean, in case of a stationary process, the output mean will be stationary, and the value will be the mean of the input times the area under the impulse response of the linear system. For example, if we assume that our h of lambda equal to e minus alpha lambda, okay, and lambda is greater than or equal to 0. So what is the area now? So the output will be mu x times the integration. Sorry. So it will be mu x times the integration from 0 to infinity. H of lambda is e minus alpha times lambda d lambda, and this will be mu x times 1 divided by alpha, okay, and the integration from 0 to infinity, at infinity equal to minus 1 minus 1, so it will be mu x divided by alpha. So this will be mu y. So it will be scaled by alpha. So if alpha equal to 0.1, then mu y will be 10 mu x. Okay. If we have zero mean input, regardless stationary or non-stationary, but we have zero mean, which means that it is always zero. The input is always zero. The mean is always zero. Then the mean of the output will be also zero, because the here would be 0 multiplied by any value will be 0. Okay, so this about the mean. What about the correlation, the autocorrelation function? So the autocorrelation function is the expectation of y at t1 times y at t2. Now, always I start by the general formula, then we come to the case of stationary or non-stationary or so on. So in this case will be the expectation of what is y at t1. It will be the integration, okay, of minus infinity up to infinity. It will be like, as we saw before, that it can be h of lambda 1, for example, times x of t1 minus lambda 1 d lambda 1 multiplied by the integration from minus infinity up to infinity, h of lambda 2 times x of t2 minus lambda 2 d lambda 2. I didn't want to put the same lambda because it can be different times in general. Now we are talking in very general form. Okay, so this will be we have double integration, as you can see. We have double integration from minus infinity to infinity, from minus infinity to infinity, and then h lambda 1 and h lambda 2, they are deterministic, so I don't care about them. So it will be h of lambda 1 times h of lambda 2. Okay, then I have the expectation of x of T1 minus lambda 1 times x of T2 minus lambda 2. Okay, then we have d lambda 1, d lambda 2. Okay, now our important part is this one. Okay, so this one actually you can either put them in the if it is non-stationary, if the signal is stationary, then you can say that just this will be r x x of T1 minus lambda 1 and T2 minus lambda 2. Okay, if it is stationary, then I will be interested only in the difference between them. So in this case will be Rxx of T1 minus lambda 1 minus T2 plus lambda 2. Okay, so by this way we can compute the correlation, the autocorrelation of the output. The autocorrelation of the output y at T1 and T2, it will be given by this equations. Sometimes it is easy to handle this integration if the autocorrelation was simple and was easy to and each of the system was easy to have analytical solution. Sometimes it is more difficult to evaluate the integration. How in this case I can find the autocorrelation of the output? Again, we can do it by finding the Fourier transform, okay, of the input square. So we take the power spectral density of the input. Then we have phi xx of f. Then we can compute phi y of f as the magnitude of h of f square times phi xx of f. And then from this one, I can have the inverse Fourier transform, and then I can find the autocorrelation function. Okay. In case that your signal is non-stationary, this will be valid only in a stationary signal. If it is non-stationary, actually you will have here the time variable that you should have it, and this will be also with the time, the output will be at certain time. Okay, this is in case of non-stationary, but for time invariant system. If the system also is time varying, it will be even more complicated because here you need to add this time tau in this h. It can be very complicated in that case to be evaluated. Okay, so let us go back to after this introduction. Let us go back to the lecture or to the book chapter to see a few examples given about this linear operation of stochastic process or of random process. Okay, so you can see that when you see a study from the book, so you will see that we have here I explained a little bit about the static system. Then we go to the time linear time invariant system. So you can see what I explained now about the superposition property, and after that I explained the direct delta as I explained it now. Then the representation of any signal by as a repetition of delta as it is shown here. So any x of t can be represented as summation of or integration of delta function. So if you know the response of the system of delta, then you can find the output for any input. Okay, so this is the concept of convolution as you can see it. Then we talk here about the properties of direct delta. So it has like uniform frequency spectrum for all the frequencies. Here we show how to find the Fourier transform of the output, and here you can see that we prove the theory of the multiplication. But of course, those are like revision for linear time invariant systems. You don't need, of course, for the course I will not bring the exam, for example, a question how to derive these, because it is not part of the course. Actually, this is not probability or something. It is more or less linear systems. Okay, so but then I expanded it for general any differential equation. So, and after that I try to connect the differential equation to the concept of convolution. What is the relation between convolution and differential equation? What is the relation between system transfer function and the differential equation representing any linear system? There should be relation, and this relation was explained here, and I show here how to convert from any representation to other representation, from convolution to transfer function, from transfer function to differential equation, from differential equation to transfer function. What is the difference between Fourier transform and Laplace transform? All these things you will find them in this chapter. After that, we give some simple example as I explained now. Okay, so you can find some examples here. Okay, and also we try to solve here some physical system that you have. Physical system, it was given in this differential equation. Okay, then here assume that the system has zero initial condition, derive the transfer function, and then by using inverse Laplace derive the impulse response. So we try to find the impulse response from differential equation. Okay, so this is one thing that important to understand by engineers. Okay, and after that, using Scilab, this is like Octave. Okay, show the impulse and step response of this system. So if input equal to this one, how you can find the output. Okay, here is the code is given. So another example and the code of that example as well. And then we go to the state space representation, and then we try to connect what we have studied so far: the impulse response, the differential equation, the system represented in the frequency domain, like Fourier transform or Laplace transform in the complex frequency domain, and what is the difference between them, and from all these representation, how to present the signal in state space representation. So we know that state space representation is very important, and actually because this book we will cover also by the end of this book Kalman filter. This is the reason that I introduced this linear system modeling, because later we study also Kalman filters, and Kalman filter and those like high order filters are based on the state space representation. So here we have the state space representation and how to convert from any signal or any differential equation to state space. I am sure that I don't know if you still remember it from linear system course or not, but it is anyhow, it is given here. It is not requested from you, of course, but I do suggest and advise you to read these things. They will be very good and refresh for you when you start and complete your master in the college. So okay, so this is all that what the state space representation, and also how to make this with in Octave or MATLAB, and how to solve them. Many examples, as you can see. Up to here is 100 example given in this 2 chapters. So, and all examples are solved. Okay, and also it was written in the code how to make the code in here it was given in Octave. By the way, Octave code is it works directly on MATLAB. So if you are using MATLAB, just put this code, copy paste to MATLAB, it will work. But of course, you might remove this. For example, here we have package load control, because in MATLAB they are already there. But in Octave, we need to upload the package of control in order to work in the state space and so on. So if you want to run this code on MATLAB, just copy paste the code in MATLAB, but remove this line. Okay. Then the stochastic process and linear time systems. So now this is what I actually was explaining now to you. That y of t is the convolution between the input and the impulse response of the system, and after that, how to compute the mean. Exactly what as I was explained to you now. Then the autocorrelation function. Okay. This is exactly as the way, and also the other alternative to compute the autocorrelation function by finding the Bose-Becker density, and from the From the Bose-Bakar density, we find the autocorrelation function by the inverse Fourier transform. And then we have here example. So assume linear time invariant system with impulse response function given by 0.1 10 of the power minus 10 of the power minus 3t ut. Where ut is the unit impulse, which means that it is equal to 1 for t greater than or equal to 0 and 0 elsewhere. The input, if the system is stationary, the input, if the system is a stationary white noise random signal with normal distribution that has 0 mean and unit average power. It means that the input of the system now, it has a stationary white noise, and it has normal distribution, and it has 0 mean and unit average power. Then find the mean and the autocorrelation of the signal at the output. Moreover, find the Bose-Bakar density of the output signal. So actually, we just apply what we have seen now. So the autocorrelation, because the input is 0 mean, so the output will be 0 mean. That's it. I will not think about that, okay? And the autocorrelation function of the output, then we apply the formula above. So we have the autocorrelation of the input times this h, okay? And it is the same if you change. So it is the same to be in this way, okay? And we said that the input is white noise. What is the meaning of white noise? As we explained in the previous lecture, white noise means that the autocorrelation is impulse because it is uncorrelated. So now we remove our xx and we put delta, the impulse direct delta function, and then we put here the difference between them because it is stationary. Okay, so it will be in this way. Now we just as we know that you can take, for example, for lambda 1, d lambda 1, and then you substitute for delta in this lambda 1. Okay, so I just explained this, how this happened. So let me go to the whiteboard again to explain those things. Even they are basic, but it is important to understand how could we do these calculations. Okay, so if you have any integration of, let's say, delta t minus 7, okay, then we have here x of t, then we have dt. Okay, so this result, what you see, you look to what is the shift here. The shift is minus 7. The shift is by 7. The shift is by minus 7, means that to the right direction. So the result directly will be x of 7. Okay, so as you see, for example, in this integration, if you have, let's say, you have double integration, okay, and then we have delta of t1 minus, let's say, t2 minus 5. And then we have x of t1 times x of t2, dt1 and dt2. This is what we have. Okay, so now you can just fix one variable. So look to t1. Let us take t1. Okay, so t1, and we have here, this t1 is shifted. It is like t1 minus t2 plus 5. It is shifted by t2 plus 5. Then you can kill one of the integrations, and the result will be still we have one integration, but instead of t1, we put this t2 plus 5. So it will be x of t2 plus 5, okay? And then x of t2 is again as it is, and then the integration will be with respect to t2. So now we killed one of the integrations because of the delta, because delta, as you can see, here we have one integration. We killed the integration because we got now the shift by x of 7. Here we have double integration. We can kill one of them by substituting what is t1 shifted by t2 plus 5. Then we substitute this one within t1. Then we have both of them now is function in t2, and we can take the integration with respect to t2. This is actually exactly what we did in the example. Yes, so we can go to that. So here we have again the same. So you can see that we have two integration, one with lambda 1 and one with lambda 2. And we have here lambda 1 and lambda 2. So we can kill one of the integrations. Here we killed lambda 2 by taking lambda 2 is shifted by t minus tau minus lambda 1. So we substituted this in the other of lambda 2. Then we have only the integration becomes only in lambda 1. And then we solve the integration. Then we got the autocorrelation of the output. We can compute the covariance of this, the Bose spectral density by taking the Fourier transform of this autocorrelation function. So by taking the autocorrelation function, the Fourier transform, we got this is the covariance, the Bose spectral density of the output. Okay. Here we show it another way to derive the same Bose spectral density, but I used the other way. So the other way that I computed the Fourier transform of the system, then I multiplied the Fourier transform of the system by the Bose spectral density of the input. The Bose spectral density of the input is equal to 1 because it is white noise. So now the Bose spectral density of the output actually, and as expected, it will be exactly the same result as we obtained by the other way. Okay. After that, here actually we have the part which I decided to exclude from this course, because this is the reason that I didn't give the Brownian motion in the last chapter, because here if we need to deal with differential equation and the input is a random process, you can see that what we did in this chapter so far, we compute only the mean and we compute the variance or the correlation function. But if I asked you question, okay, for this system or for this example, what is the probability? Okay, let me write it here. What is the probability that the output yt at time t to be, for example, less than or equal to 1? Actually, you will not be able to solve this basis, because here what I explained, I mean, you cannot solve it directly, but of course you can do it. That if we complete the discussion, but till now we compute the mean, and we compute the autocorrelation function of this output. So we have the autocorrelation, we have the mean, okay, but we didn't show what will be the distribution of the output. If the distribution of the input is Gaussian, of course the distribution of the output will be Gaussian as well. But what will be the variance of the output and how the variance will be changing with time? So all these things were excluded from this course. Even they are important, but actually I feel that it can be too much if we study this part as well. But it is very important because you can see here, if we have differential equation as this one, and we know the distribution of the input, how will be the distribution of the output? For example, you have this differential equation, okay, and if alpha t is a random process, how we can handle this differential equation? The conventional way of solving differential equations is not working here. So we need to develop a new kind of differentiation. It is called Ito integral, for example, in order to handle these problems. But as I said, this is not included in this course. So we stop here. Let us stop in how to compute the mean and the autocorrelation of the output of linear system, if you know the characteristics of the input signal. So this would be enough, and hopefully this will complete the picture that or the objective of this course. Okay, so now I open the discussion. So if you have questions about today's lecture, do you have any questions about today? Okay, I will stop now the recording, so and we open the discussion because the lecture.
نعطيك وقت شوي عشان نطلع على